So this is our today's next problem. A fixed beam AB of span 6 meter carries uniformly varying load of intensity 0 at end A and 20 kilonewton meter per meter at end B. Find the fixed end moments and draw the bending moment and shear force diagram for the beam. Okay. So let us see first of all what is the loading diagram from the given description. This is the loading diagram. Zero intensity of loading on support A and 20 kilonewton per meter intensity of loading on support B. Okay. Now our aim is to find fixed end moments on supports A and support B. Okay. A and B. So MA and MB we have to find. Now as this is a varying load. We have already solved one numerical in the last session, which involved varying load. So there the approach of integration was done. So similar approach we will keep here also. Okay. So since this is UDL, again we are going to consider one origin. So our origin will be on support A. From this origin, we are going to take a section at a distance x, and it is the distance of the elemental strip that we have considered here. Okay. So for this strip, now there will be a varying load and its intensity is 20 into x by 6. This is different. Now how is this 20 into x by 6? We have considered the elemental strip of length dx. Its distance is x from support A. So as you can see, as you go on increasing the distance from support A, the intensity of loading goes on increasing. It varies, correct? And up to support B, it is 20. So if you see how to find this intensity of loading at a distance x, so it is simple cross multiplication. So we have two things. One is when span is 0. When span is 0, we have intensity of loading as again 0. Okay. Next, when there is 20 meter span, 6 meter span, the intensity of loading is 20. So when there is x distance or section considered is x, what will be the intensity of loading we have to find? Okay, we have to find this question mark. So how will we find? We will take simple cross multiplication. This one. Okay, so 20x is equal to 6 times the unknown term. Okay, 6 into, let us say, uh, y, 6 into y. Okay, so we have to find y value. So y will be from this 20x upon 6. So intensity of loading uh, for a distance x is 20x upon 6. Now once we have considered or assumed this intensity of loading at the assumed section x, now what we have to do, we have to treat this 20 into x by 6 as the point load. Okay, so this is intensity of loading. You multiply this by dx, you will get this total load as point load 20x dx upon 6. So that will be your capital W. Now when there is point load acting on a fixed beam, eccentrically acting, then in that case we have our fixed moment equation as WAB square upon L square for fixed moment on support A, and WA square B by L square for fixed moment on support B. So we already know this equation from first principles. Okay, WAB square upon L square. Now this is partial moment because W is partial load 20x dx upon 6. So we have substituted 20x dx upon 6 as W. Then the distance of this strip from support A is x, which is nothing but A in this equation, and B will be total span minus x. So 6 minus x. So as there is B square in the equation, we will have to substitute this as 6 minus x bracket square totally divided by L square. L is the span, 6 square. So now we shall simplify this. So 20x into x is 20x square into 6 minus x square dx upon 6 cube. Okay, this is 6 square already in the denominator. This 6 will come to the denominator. It will add up. So it will become 6 cube. Okay, so this is dma, and dmb will be WA square B by L square or WBA square by L square. Here MB. So partial moment for uh, fixed support B is dMB, and its formula is WA square B by L square. So uh, again W is 20x dx upon 6. A distance, it is x. Okay, A square, so it is x square, and B is 6 minus x divided by 6 square. It is equal to 20x cube into 6 minus x dx upon 6 cube. So this is partial moment equation for support B, fixed end moment. Okay, now uh, we have to find final fixed end moment for support A, which will be nothing but integration of dma. What is dma? It is here 20x square upon 6 cube. 6 cube is 216 into 6 minus x square dx. So ma is equal to 20 upon 216 into integration of 0 to 6 of the term that we have expanded. We have taken now 20 upon 216 outside the integral. X square is as it is, and 6 minus x bracket square we have expanded. So it is 36 plus x square minus 12x. So it is equal to further 20 divided by 216 into, now I have multiplied x square to the bracket. So 36x square, its integration is 36x cube upon 3. This is first term. Second term, x square into x square, it is x raised to 4. So its integration is x raised to 5 upon 5. Third term is minus 12x into x square, so it becomes minus 12x cube. Okay, so its integration is minus 12x raised to 4 upon 4, and its limits are 0 to 6. So we have substituted all the appropriate limits, and we have simplified further, and we have found that MA is 24 kilonewton meter. Okay, MA is 24 kilonewton meter. Now next is MB. We have to find MB. So MB's equation, DMB equation, partial fixed end moment. Again, we have got this from the uh, elemental strip and so on, and then we have integrated. So now we have to carry out the integration. 20 upon 6 cube is 20 upon 216 taken outside the integration, which is constant, and x cube we have multiplied this to the bracket, so 6x cube minus x raised to 4. So its integration is 6 x raised to 4 by 4 first term minus x raised to 5 by 5. So limits are 0 to 6. So MB is 36 kilonewton meter. So we have found the fixed end moments on both the ends. Now we have to draw SFD and BMD. Now this is a relatively new part. However, drawing SFD BMD is actually not a new part for us. We have already seen this in SOM. However, this requires a little bit different approach. Let us see how. Here we have to draw free BMD. Free BMD is WL square upon 9 root 3, which is from the knowledge of strength of materials. So 20 into 6 square upon 9 root 3, which is 46.18 kilonewton meter. So it is a cubic parabolic curve, and uh, maximum moment will take place at 6 divided by root 3 meter from left end A. This is also we know how to find. Okay, so I will not discuss in details about this. MA and MB, we have found fixed end moments. So this is our BMD with overlap. Okay, or BMD with overlap. However, I am not in favor of representing BMD with overlap. It is always better to draw bending moment diagram on tension side. Okay, what is the net value? Because if you see, the blue line is only positive BMD, this one, and this red line is all negative BMD. All the portion in between these two, here it is not effective. Which is effective? This part, then this plus area, and this negative area. So only these three parts are effective. This 46.18 is from this red line, this total value. However, only this part is effective. So how much is this value? We will have to find using calculations. Okay. I do not suggest drawing BMD by overlapping. Now I want to calculate support reactions. So my fixed end moments are here. This is 24 I have shown here. Okay. And this is 36. One is anti-clockwise, another is clockwise. Okay. Now we will have to bring into picture these fixed end moments also. So these are two moments that have come into picture apart from the external loading. Okay. And support reactions we have to find. So how will we do? We will take summation of moment about A is equal to 0. Now we will apply simple conditions of equilibrium one by one. So summation of moment about A, from this we will get this equation of equilibrium. So RB into 6 into RB into 6 plus uh, 24. So here is 24 plus 24, it is equal to why are these two on left hand side? Because both the moments are anti-clockwise. RB into 6 and 24. Okay, so anti-clockwise moments are equal to clockwise moments. So uh, now clockwise moments, which are they? One is moment due to this varying load, and another moment is 36. So 36 is here, plus how to find moment because of this varying load? Find out what is the area of this triangle, half base into height. So half into 6 base, height is 20, into its centroidal distance from support A is 2/3 of 6 meter. Okay, h by 3 from base and 2h by 3 from apex. So apex is here. So it is 2h, which is 2 into 6 divided by 3. So RB is 252 upon 6, which is 42 kilonewton. Then you find reaction at A as 18 kilonewton. Then we have to draw shear force diagram. Now we have found reactions, and please wait 1 minute. Shear force on A is 18 kilonewton. Now, since the loading is varying load, so the variation of shear force diagram will be parabolic, and shear force on support B is minus 42. Now we have to consider here the sign conventions. Left hand side and right hand side of the section, upward forces on left hand side will be treated positive, upward forces on right hand side of the section will be treated negative. Okay, so if this is the section that is considered XX, upward force on right hand side of the section will be considered negative, so minus 42. Now it is changing the sign from plus to minus. So at what location is it changing the sign? Here somewhere. So we have assumed this distance as x, and we have taken shear force at distance x6 at 0. Okay, and we have written the equation for shear force on this distance. So after uh, writing the equation and solving it further, we have found that x is equal to 3.29 meters, where the shear force is changing its sign. Now what will happen at this point? At this point we will get maximum bending moment. So we have to now find maximum bending moment, and it is 6 by root 3, which is already found. Okay, which is already found, and that is 46.18, but it is not effective moment. It is not effective moment. So at this section you take uh, summation of moment on left hand side, and then you write the equation and find out maximum moment.